Log on, tune in, find out. Another good idea from Cambridge.
I was told to chair the event seminar program. So today's speaker is Professor Peter Hydon from University of Surrey. He speaks on conservation modes via the variational difference complex.
Thank you very much. And thank you to those who organised this wonderful, wonderful conference for inviting me. This is work that I've done jointly over the last 10 or 11 years. In particular, my closest collaborator, Liz Mansfield, contributed a fair amount to the variational difference complex part of the talk. Now, I'm not going to say a lot about that because it's quite technical. I will just say, however, if you need to talk to someone, if you need an expert in algebraic topology, go and see Liz Mansfield. She knows everything. So my former student Sasha Razin, who's now at Bar Ilan, and current student Tim Grant have also contributed to this. So I became interested in symmetries of difference equations in around 1998. I'd been focusing on differential equations up till then, and I thought it's strange that there wasn't a system, a set of techniques that one could use for difference equations in the same way that you could for differential equations. At the time, the state of the art was somewhat mixed. That is to say, people had found symmetries using Ansätze, Maeda in particular, kick things off there, using known functional identities. Orphanidis, and I'm grateful to Frank for this, was interested in the discrete sine-Gordon equation and used known functional identities on sines and cosines to find some conservation laws. Another approach embedded the problem into a continuous one. So rather than taking a discrete independent variable, you said, suppose the independent variable is continuous. And Reinhard Quispel and his collaborators had some success with this and were able to use series expansions to consistently find some symmetries of difference equations. And then there was the non-local approach, where one thought about a difference operator as basically an exponential of a derivative and then expand out in an infinite series. And that was the approach pioneered by Levy and Vintonitz. Lastly, because this is an integrable systems conference, although I'm not specifically restricting attention to integrable systems, there were, of course, the major contributions coming from people who were using properties of integrability, so looking at the lax pair and so on. So there's a question, can one deal with symmetry analysis, finding conservation laws and all the other things that go with it, without making these simplifying assumptions? When I say simplifying, in some cases it makes the work quite a lot harder. And to show you that it is possible, if you haven't seen this sort of thing before, I just want to do a very simple example, the discrete potential KdV equation, and I've taken the parametric dependence out just for simplicity in this example. So there's the equation, and the usual thing for symmetries, you look for Lie point symmetries, so these are going to affect only the dependent variable u, the only continuous variable. They're going to have no effect whatsoever on the discrete variable because you can't move a discrete variable an infinitesimal amount without embedding it in a continuous problem. I don't ever want to do that. I always want to take discrete problems on their own terms. And so you get the linearized symmetry condition, which just amounts to linearizing that equation. And the problem with this and with the symmetry condition generally is that it's a functional equation. And so the techniques that people had introduced got around this by using identities or expansions or whatever. But you can actually just solve that functional equation directly. And the technique is very straightforward. We want to replace u11 by the right-hand side of equation 1 there. And that gives us something with a horrible mess. The q depends on the continuous variables in different places. But there are 3 continuous variables, u00, u10, and u01, which when you've substituted for u11 appear in the linearized symmetry condition. So you could apply a differential operator to eliminate some of the q's. And the optimal operator to apply is this one. Not only is the right-hand side of 1 invariant under that operator, so this term goes, but also u00 is invariant under that operator, so this one goes as well. And you're going to get something that involves only those 2. And so you get a functional differential equation. Do the same thing again. This time we've got only 2 continuous variables in there and differentiate with respect to one of them to get, well, in this case it's an ordinary differential equation. And then it's just a case of integrating back up, solving the chain of functional equations that you get. It's very straightforward, and you eventually come back to the linearized symmetry condition. So the idea is to take the original functional equation and to construct a chain of functional differential equations, necessary conditions that follow from the original one. Then to go back up the chain when you've reached a partial differential equation in general, and if necessary there may be some extra branches of the chain in a more complex problem, but you ultimately finish. It's an algorithm, it closes. So the same process can be applied for any old symmetries. You don't have to have point symmetries. Your characteristic Q may depend not only on KL and U00, but also on higher shifts of the independent variable. I'm only going to illustrate my talk with two independent variable problems. We have had a look at some 3 independent variable problems, and I'm happy to talk about those afterwards if you want. So the process is basically the same every time. You write down the linearized symmetry condition. For this sort of equation it looks like that, where omega subscript 10 means the derivative of omega with respect to u10. Apply appropriate differential operators to reduce the number of unknown functions, to reduce the number of q's, and eventually you'll get down to a PDE. Back substitute, going down any extra branches as necessary, and solve any difference equations that result. Now these are always linear difference equations because the original condition is linear, but they may not be necessarily easy to solve. The biggest problem with this approach is expression swell. As you keep differentiating, you get more and more terms. You have to do it with a computer algebra package, and it quickly becomes difficult. Potentially, there is difficulty in solving the linear difference equations that might arise when you back substitute. And I can give you an example of that, but it's a rather trivial example. In all the interesting nonlinear problems that we've looked at, the difference equations have always been easy to solve, and that's been your experience as well. Yeah. Okay, so here's an example of a more generalized type of symmetry. Symmetry on a 5-point cross, again for a quad graph equation, and so we're using the quad graph to eliminate the gray points and just to have those as our initial conditions. And each such symmetry splits into something that's defined only on the horizontal line and something that's defined on the vertical line. And that holds for all of the ABS equations. ABS, Adler, Babienko, Soros, the integrable equations in their famous classification. I didn't mention parameters in my simple example, but the ABS equations do contain parameters, and in general you might want to incorporate variation in parameters. To be consistent with consistency on a cube, the only thing the multipliers of the derivatives in the parametric directions, the only thing they can depend upon is the parameter itself, whichever one it is. So, for instance, I'm using all the time the simplest examples. Discrete potential KdV. You've got 9 generators, some of which we've seen before as point symmetry generators, some of which are horizontal, some of which are vertical. And coupled with these 2 higher order symmetries, there is with each one a master symmetry. This involves K or L, the independent variable in the symmetry explicitly, and also involves a parametric derivative. So, to summarize the symmetry, this isn't really a talk about symmetries, but it's easiest to explain the method in the context of the symmetries. To summarize what happens with symmetries for the ABS equations, every ABS equation has a horizontal generator of this form and a corresponding master symmetry of that form. And the master symmetries therefore each generate a hierarchy, an infinite hierarchy of symmetries. The ABS equations with constant coefficients, I'm emphasizing, all have infinite many symmetries. And there is also a vertical hierarchy of symmetries, so there's actually a doubly infinite hierarchy of symmetries for each ABS equation. If the parameters are not constant, there is trouble, and the only horizontal 5-point symmetries are in fact ordinary point symmetries, and true also for vertical ones. With most of the ABS equations, you can rearrange the master symmetries in such a form that you don't actually change the parameters. So if we go back to the one I had before, whoops, gone a bit fast, we could take x8 plus x9 plus x1 to eliminate the parametric derivatives. And you can do that with almost all of the ABS equations, but not with the 2 most complicated ones, Q3 and Q4. So that's sort of a rough summary of certainly the things that we've contributed to this, and there are many other people who've contributed, and in particular the group at Patras. What's a conservation law? Can we do the same thing with conservation laws? And it's not a silly question to ask that. For differential equations, everyone knows what a conservation law is. It's a divergence expression that vanishes on solutions of a given differential equation. So for difference equations, what would you do instead? Forward differencing, backward differencing, centered differencing, something else? Well, all those expressions can be written in this form. Shift forward minus the identity of something summed over all independent variables. SI is the unit shift forward in NI. I should have said that. But the question has been put to me by Frank earlier, why not use equivalent expressions? Why not use a multiplicative form? And certainly if you're going to look at analytic properties, things may be very different. This one can obviously be converted to that one by taking logarithms, but you might wreck anything analytic in doing that. Well, I'm largely an algebraist, so I don't care. But that's not really a very satisfactory answer. And I think what a more satisfactory answer is comes from algebraic topology. Differential conservation laws are elements of the kernel of the Euler operator. Divergences are killed by the kernel, and on a topologically trivial domain, the kernel is precisely the set of all divergences. So for differential equations, we have a variational complex, and the normal de Rham complex goes along the bottom. dH is just the normal d, but applied to independent variables only, the normal exterior derivative. And so if you apply any of these operators, a pair of them, you get 0. The kernel of one operator is a subset of the image of the next. And you can calculate the cohomology groups, the factor groups of the kernel by the image of the previous thing. The cohomology groups depend only on the topology of the domain. And when we get up to volume forms, when we get to the end of our independent variables, there is an operator, the Euler operator, which is basically the standard Euler-Lagrange operator, but applied to functionals rather than to functions. And this then continues the complex on, and the next operator in the sequence is the Helmholtz sequence. This is well known. It's in Peter Olber's wonderful yellow book. And divergences are precisely the elements of the kernel of the Euler operator on topologically trivial domains. Now, it would be wonderful if we could do the same thing for difference equations. And we can. It's taken a while, but we can. Difference operators produce a variational complex, pretty much the same as this, but with something that takes differences, replacing the exterior derivative. So this is an exterior difference operator, and again it takes k forms to k plus 1 forms in exactly the same way. Now, the nice thing about this is everybody has always been agreed on what the discrete Euler-Lagrange operator is. Easy to calculate the operator for variational problems. There's never been any conflict about this. And so to have something that you could append onto this, replacing the continuous chunk with a difference chunk, would seem to be a sensible thing to do. And it turns out then that the kernel of this Euler operator, the Euler-Lagrange operator that everybody knows for difference equations, is the set of all things of this form, that left-hand side. So that's standard form for difference divergences. Okay. So I'm not going to show you the nitty-gritty. It's just, it would be another talk to do that. But just the key features. dH is replaced by a difference operator. When you do that, the algebraic structures actually go across unchanged. Now, this is quite remarkable to me because we've thrown away continuity by sticking to purely discrete objects. Continuity is gone, and continuity is so fundamental we use it without thinking about it most of the time. Turns out it doesn't affect the algebraic structure whatsoever, and you can replace continuity by ordering and retain the same algebraic structure, which means actually that you could build the de Rham complex on the ordering property of the real numbers, not in the standard way, using the topology of Rn. It's just an interesting little observation. If you're taking a problem on a differential equation or something and you want to discretize it, if you're a numericist, this tells you, this discrete, this difference variational complex tells you that you get precisely the same cohomology groups provided you use enough points. And that's sort of obvious, really. In other words, you have to cover your domain with enough points to capture any holes that there are, to capture any other topologically non-trivial things, and then you'll get the same cohomological behavior. Okay, so that's all I want to say about the difference complex. But it does lead to this definition of the conservation law as being the most obvious one. So the problem that we have is to find a basis for the vector space of all equivalence classes of conservation laws. So what's an equivalence class? A conservation law is trivial if it vanishes either identically without reference to the difference equation. The typical example is a total curl, or if its components vanish on solutions of the equation. In other words, you don't need to take the divergence to get something that vanishes. Once you factor out those two trivialities, you have an equivalence class. So two conservation laws are equivalent if their difference is trivial. And that problem is just too hard. It really is. So we'll start small. And small means for quadgraphs that we start with a conservation law where f and g depend on just 3 points, u0, 0, u1, 0, u0, 1. And we're going to shift f forward and shift g forward. So we just use the equation on one tile. So then the determining equation is that the divergence of this should vanish on solutions of the equation. If I write u11 is omega, which is a function of all the other variables, then that goes into the equation like this. This is just a functional equation of the same sort that we saw with the symmetries. The only differences are that it depends on, it has two unknowns, f and g, and it depends on more variables than the simple point symmetries do. Apart from that, it's a simple functional equation. You can treat it in the same way. The nicest thing to do with this sort of problem is to apply these two commuting operators. Now, these things differentiate. This one differentiates with respect to u10, leaving omega invariant. And this one does the same with u01. So in other words, when we differentiate with respect to those things, we are going to kill off, with one term, we're going to kill off this one. With the other one, we're going to kill off this one. Okay? This one, if we differentiate with respect to u10, leaving omega invariant, that one goes. And because they commute, it doesn't matter which one we apply first, and therefore we don't get any expressions. Well, so that's very neat. That immediately gets us down to something that is far more manageable, and then we can just apply ordinary partial differentiation to reduce that down, and it always comes out as a PDE of order 5 or less. Easy to show that. For the quadgraph equations classified by Adler, Babenko, and Soris, the D4 symmetry that they include in their classification gives some extra help. It gives us some extra equations which simplify things a little. For some quadgraph equations, like discrete potential KdV, you can go a little faster. So you can apply operators that are more effective than they should be, but you'll always get there in the end. And for that equation, there are precisely 4 conservation laws on 3 points. Okay. The other ABS equations, there are 3 more with 4. That's the cross ratio equation, discrete potential modified KdV, and A1 delta is 0. Several of them have one conservation law only of this form, and others have 2, and that's the complete list. And so you can find conservation laws for higher order problems. You just say, how much do I want my f to depend on? How much do I want my g to depend on? Use the equation, and it shifts to write the conservation law on some initial conditions. Okay. Now, typically, it will be a cross of initial conditions. You could use a staircase, and I'll say something about that in a minute. And you then continue exactly as for symmetries. But again, the biggest problem is expressions well. So if we're looking for 5-point conservation laws, we're going to, if we do it on the staircase, involve 2 tiles. If we do it on the cross, we involve 3 tiles. Now, the staircase works very nicely when you've got arbitrary omega, and in particular, when omega is not solvable, when u11 equals omega is not solvable for the other u's. You should use the staircase because you're going in the right direction. Sorry, that way as you're looking. On the other hand, the ABS equations are solvable for each variable, and therefore we should use that structure, and this gives us a quicker way. So discrete potential modified KdV has the following conservation laws. These are logarithmic rather than the previous ones were all rational polynomials. And you can see that there's quite a nice structure here. They are basically of the same form, one's horizontal, one's vertical in some sense, and they're multiplied by k and l respectively to give you another one. That's true for every ABS equation with constant alpha and beta. There may be more. Now, this is where we were running up against the limits of computer algebra. For Q4, we couldn't classify all conservation laws on 5 points. We found 3, but that's not to say that there isn't more. However, I think it's unlikely. Q4 spawns the other equations, and the other equations don't have that. Okay, so that really is the limit at the moment. But we could use the action of symmetries on conservation laws to give us new conservation laws. And in particular, if we apply the master symmetries to a given conservation law, we will indeed get a new conservation law every time. I spoke about this in Leeds a couple of years ago, and Sasha Mikhailov said, well, isn't it guaranteed that your master symmetries will always give you new conservation laws? And the point is, at that time, we didn't know. In fact, we still don't quite know, but we more or less know. Because you have to check that conservation laws are independent. Just because it looks independent doesn't mean it is. And this is something that's very easy with differential equations. You just look at the order of the highest derivatives that are there. With difference equations, you can be misled, and I'll give you an example of that. So apparent novelty has to be checked, and there is a way of doing this now using characteristics of conservation laws. So what's a characteristic of a conservation law? Well, for a differential equation, scalar PDE, I'll call it delta is 0, any conservation law can be written in the form divergence of some vector is p times delta. Okay? If you take a given conservation law by integration by parts, you can always put the conservation law into that form. And Alonso proved that there is a one-to-one equivalence between these conservation laws and the characteristics P. Not between single ones, but between equivalence classes, where two conservation laws, as we know, are equivalent if they differ by a trivial one, but two characteristics are equivalent if they have the same value on solutions of the equation. So if we substitute delta as 0 into p, we're going to get the same result, whatever form our characteristic originally is in. So the question is, can we do the same thing for difference equations? And Reinhardt and Maruno in 2006 said, yeah, easy. If you have a polynomial conservation law, and they have some examples in their paper. And this is how to deal with the general case. If we've got a difference conservation law, I'm going to write it in the form, in this form. So here, Z denotes all the things I'm not going to eliminate, and delta is the difference equation. Delta with brackets around is the difference equation, and finitely many shifts, as many as we need. So you could regard Z as being the initial conditions and the independent variables. They're all the things that don't get eliminated. And that's going to be 0 on solutions of the equation if C of Z and bracket 0 is 0. In other words, you substitute delta is 0 everywhere. And the way to proceed is to use the homotopy idea. So we just use the fundamental theorem of calculus to write C, bearing in mind that when we put Z is 0, it vanishes, to write C as this term. This is just the derivative of C of Z and lambda delta with respect to lambda. Okay? At that stage, we've got some set of shifts of delta, so we can sum by parts. If we sum by parts, then we get delta coming outside, and we get S minus j, the backward shift in the j direction of this term. Now that looks like an Euler-Lagrange operator, and that's exactly what it is. But it's not the general Euler-Lagrange operator where you're varying u. It's the Euler-Lagrange operator where you're varying delta only. You're treating delta as an independent variable. As a dependent variable and varying that. So that's the Euler operator connected with delta. And then when you've formed that, you replace lambda by lambda, delta by lambda, delta, integrate over lambda. And this is just some extra terms that come out of the summation by parts. Okay? So that gives you an equivalent conservation law. Div f tilde is 0 when lambda is 0, and this is now in characteristic form. That thing under the integral sign, or the thing with the integral, is the characteristic. So the difficult part is not the defining of the characteristic, it's proving Alonso's theorem for difference equations. And it is messy. I won't show you the proof, but it's been done. Here's an example of what I meant about potentially being misled by the appearance of a conservation law. For the parameterless dp kdv, I'm going to define delta to be that. This is a conservation law on 5 points, not on the cross, but on a step. And that's fine. But the characteristic, if you work it out, is somewhat simpler than the appearance suggests it should be. And that's exactly the same characteristic as for this conservation law. And so the two conservation laws are in fact equivalent. Okay, so I think this answers the question of how can you tell whether or not there are infinitely many conservation laws of a given equation that can be generated by master symmetries. Quite independently, those who were at Sasha Razin's talk a few weeks ago, he and Jeremy Schiff have used a Gardner-Green method to construct an infinite hierarchy of conservation laws, not using the master symmetry approach. And so we know already, or we knew already from their work, that there are infinitely many symmetries, conservation laws of dp, kdv, but this approach can be applied to all the other ABS equations. Okay, so to summarize, for each of the ABS equations with constant parameters, just going at it directly with brute force yields infinite hierarchies of symmetries, low-order conservation laws up to 5 points, and the possibility of generating higher conservation laws, and certainly the ability to test whether or not they're independent. We weren't able to answer the question, are there higher order symmetries of conservation laws, but certainly there are no 5-point symmetries or conservation laws when A and B, alpha and beta, are not constants, apart from the ordinary point ones. So, open problems. Well, can we answer that last question? Are there any? A computational problem. When I did the little trick in the opening example, using that particular differential operator that got rid of 2 terms, that was optimal. That was better than you might expect. Normally you would expect to lose 1 term with each differentiation. Is there a way that we can take this approach and apply it algorithmically? Can you get a computer to be able to work out which is the best order to do successive differentiations in order to be able to deal with complex problems without tripping over? And perhaps more generally, as people are starting to think about difference equations on general graphs, what happens when we look to things that are not ordered on a single variable z at a time, but when we've got just some connectivity between them? Is there an analogue of the difference complex for that? There should be. I'm sure there should be. And what does integrability imply about the structure of symmetries? And this is where Pavlos and Basilis have begun to make quite substantial inroads into answering how integrability affects the sorts of symmetries that appear. And so I'll stop there.
Are there any questions?
Yeah.
You say something about alpha and beta not constant. ABS.
For the ABS equation.
You have your parameters given with the parameters.
Mm-hmm. But you can have
only by constant and non-constant.
Okay, so
for the lattice.
The cube consistency on a cube allows you nonetheless to have alpha depending on one of the variables, beta depending on the other one.
That's on the cube.
They don't have to be constant.
Well, once you put that on the lattice, when you look at the two-dimensional,
yeah.
What is the alpha?
So alpha would be a function of k only, and beta would be a function of L only. Yes. Yeah.
It's a bit not a bit artificial.
No, as far as I'm concerned, I really don't care about integrability. I mean, I shouldn't say this at the Discrete Integrable Systems conference, but it's just an equation.
Say there is no symmetry if you start having these alpha and beta non.
There are no higher
symmetries.
Yeah.
Is that definitely not integrable? For example, the Hirota-Miwa equation with such dependence is integrable.
No. maybe not for arbitrary.
Any other questions or comments? Oh, okay.
Sorry. So I'm interested in the reductions.
Yeah.
Have you used these symmetries to obtain the reductions of these equations?
One or two, but really, that's not really been the area we've been focusing on. So we've done it because referees have asked us to include a reduction or two in papers, but that's really been the only motivation. So it would be good to talk with you about how one might generalize these things.
Any other questions? If there is no further questions, let's thank the speaker once again.